Awesome, thanks. Happy to be here. So, well, first, it's a brain of a mouse. It's technically a retina of a mouse, which is a part of a brain, but it's okay. We're getting to human brains. Actually, we have a new project being announced on Monday that's mapping large-scale MRIs of human brains. So, super stoked about that. But before we get into it, I just want to kind of reflect with you guys a little bit kind of on the story side of VR. You know, I was out in the lobby area trying the Gear VR from Mythbusters, right, where you're swimming around with sharks. I don't know if any of you guys, any of you guys try that one? No one tried it? Okay, I mean, it's gear, but it's still pretty good. And, you know, there's this one point, they put a bait thing over by this ship, and at first there's a couple sharks, and then there's like a lot of sharks, of huge sharks swimming all around you. And at one point, Adam Savage goes, yeah, I almost feel like I need to bring my arms in close. And I realized that I was standing like this. And I think it really illustrates this really powerful piece of VR that, you know I wasn't underwater and I know I wasn't really in danger of sharks, yet the immersivity of it makes there be a discrepancy between what I know and what I feel. You know, VR, as you guys all know, is this new medium of storytelling, and you're not really telling a story, you're now an agent, right? You're not even a viewer anymore, you're a visitor. It's incredibly exciting and engaging, not least for, you know, the cinematics and the exploratory experiences, but for something that I'm personally very passionate about, which is complexity. You know, VR is an incredible medium for showing the huge, right? Those VR experience where a gigantic dinosaur comes walking by, or a huge alien spaceship comes and like lands right in front of you. Things that are way too big for any 2D screen, things that you have to look around to even take in. And in the world of complexity, and particularly the world of the brain where I work and where I love, I mean, we're dealing with a huge several orders of magnitude of layered intrinsic complexity. And we need really, frankly, all the dimensions that we can get. And VR is taking us away from the 2D screen, and it's immersing us. You know, the brain is this complicated object. It's something like 80 billion neurons. There's 100 trillion synaptic connections, junctions between those cells within it. It's crazy complicated. You know, these are just a few of the branches of like 17 different cells. And if you lined up the branches of all the neurons in your brain end to end, they would stretch from the Earth to the moon 10 times. Like, it's crazy. It goes all the way from the cantaloupe size-ish, you know, of your whole brain down through macro circuits and individual circuits all the way down to the level of the synapse. And it's the activity, the electrical and chemical activity flowing through these circuits in the brain that allows you to do what you do, to recognize the words that I'm saying and to understand them, to appreciate an incredible virtual reality experience and remember it, and then relay that memory to another person who can then somehow understand it without ever even being in it. Not to mention things like not falling asleep, hopefully, or not falling out of your chair. You know, this complexity is pretty incredible. And so a couple of years ago, when we tried the first DK1, we got really excited. I got tremendously excited and started imagining, you know, what if we took these neurons from the nanoscale and we made them gigantic? You know, we made them extend far out in front of you, and synapses that were these teeny tiny little, just like almost negligible dots suddenly became these giant 3D structures in front of you. So we created our first VR experience for the TED conference back in 2013. It was so early that it was pre-Oculus acquisition by Facebook. And over the years, we've been really interested in how can we use VR as a visualization mechanism. And so I'm pretty excited to share with you guys that, you know, 2 weeks ago, we created the latest iteration of our virtual reality experience called BrainVR. And we debuted it at Tribeca Film Festival. It's actually upstairs. So let me show you guys a really quick little snapshot of what it's like in the brain. generally the gist. And we're really excited, actually, because that's the first working neural circuit that's ever been put into VR. And it represents a significant step forward in the visualization of neuroscience. You know, we have learned more about the brain in the past couple decades than in all of human history combined. You know, we are able to look closer, faster, see the brain in higher resolution. And while this is incredible, it's kind of coming with a number of different externalities, not least of which that most of the new 3D models that we have are like sitting on lab servers, because researchers are busy doing research. And, you know, computational biologists or you know, neuroscience researchers are not really, they don't have time or energy or resources or team to create these experiences that showcase their research to the world. And the other side of that is that, you know, before we can visualize things about the brain, we kind of have to know them, right? Now, only a handful of the brain circuits have been mapped at this resolution, and that's in part because it's really, really time consuming. We can generate data sets much faster than we can analyze them. And while on the one hand, we work on AI, it's more like savant AI that's sort of good at doing one thing, which is mapping out the 3D structure of neurons at the nanoscale, but it's not really that good. It still takes us dozens of hours to reconstruct one neuron, dozens of hours of expert time. And so that's why we looked outside the world of neuroscience, specifically to the world of games, you know? We needed somehow to find people who had a lot of time to spend doing something, maybe over and over again. And maybe if instead of shooting birds, you might be helping researchers. And you know, games are so ingrained in human history. You might say they kind of tell a story of how we've developed rules and structure to interact and compete without killing each other. And while a lot of elements of society are not so clear that they're a game, you know, even on Facebook, you get a score. There's not a leaderboard. It's just presented as a news feed, right? So we've drawn inspiration of these subtle game mechanics to create iWire, which is a game to map the brain. And before I show you iWire, I just want to preface by saying that that circuit that you saw in BrainVR was actually discovered by gamers from all over the world. And it was published in Nature in 2014. And Alex Norton is in the audience, who played a pivotal role in designing that. And it's actually designed to be modularized so that as we discover new circuitry, we can replace them and show people that there's lots of different types of neurons. They come in different shapes, different sizes, and they have different functional profiles. And it's the combination of these different intricate cells that allows the brain to actually compute and process information. So this is iWire. This thing rotating is one of hundreds of neurons that our gamers have reconstructed. That big blob thing there is the soma, it's the cell body, and the branches are the dendrites. As I'm scrolling through the leaderboard, it's showing you which individual sections of the cell were mapped by each player. And we have real-time chat. At any given time, there's 50 to 100 people online. We also have a pretty robust player representation system. It gives them their stats, their accuracy on the easily and more advanced cells. And this launched in 2012, and so far we have 220,000 players from 140 different countries. So this is how you actually play the game. When you go to start playing, it zooms you into a cube. Now this is a tiny volume of brain. And as I scroll through on the right-hand side, a plane is moving. And those gray boundaries are the cell membranes of neurons. What you're trying to do is kind of color inside the lines. Except when I color on the right-hand side, when I color on the gray part, you'll see that in the cube it adds a little 3D chunk. So that's what the computer software basically has added. iWire is this breakthrough project where it's humans working with AI, and together their insight allows them to reconstruct the entire neuron. So the goal of iWire really is to map one branch of one neuron from one side of the cube to the other. When you think you're done, hit onward, it takes you to a new cube. And there's all sorts of kind of advanced roles and actions that you can take as players level up through the game. They stop interacting purely within the cube and they start interacting in the overview. They actually have a sophisticated consensus system and a set of checks and balances. So in this cube, everything that's orange has been done by some of our advanced players, and they team up to actually edit errors from the overall majority of iWire. Now, it's not a singular project, in this field called citizen science, where researchers are crowdsourcing data analysis or data collection. There's a number of other projects like this. However, this is the only one in neuroscience. And it's one of the few, at least one of the largest and fastest growing games. And we really, we're not quite on the level of Angry Birds. In fact, we're far from that. However, we are drawing inspiration from outside the world of neuroscience. And a great caveat of this citizen science space is that in order to do our science, we're reliant on gamers. They're a part of our lab. They're our players. They're not users. We know them because we talk to them in chat, in real-time chat. And if they don't play, we don't make discoveries. So we're kind of beholden to them. And it is a great encouragement to us to create, these beautiful images and animations and virtual reality experiences, because most people have only ever seen artistic interpretations of neurons. They've never seen what we know. And I personally think that when you get an interdisciplinary group of people who maybe don't have a formal expertise, but what they do share is a common passion on a specific subject, then you can never really know what they're going to bring to the table. But if students don't understand what we don't know about the brain, or if someone who's just a hacker on the side doesn't understand that they could build bots or help us create better AI to analyze this software, then they can't help. And so I just want to kind of thank the whole team and also our players, the heroes of neuroscience. And we've got a number of other projects in the works, and so I hope that BrainVR expands from the circuit level. And I think what we'll see in the future is VR becoming a regularly used medium for neuroscience and other fields of science to spark curiosity, to catalyze ideas, and to just get people stoked on the wonder of understanding the world. Thank you.